for looking at the scientists through history who helped develop the atomic theory as we know it and understand it today. So the first person that we will talk about is Democritus. He is a Greek philosopher. And so history books have him on Earth in ancient Greece from around 460 to 400 BC. So not a whole lot of technology available at that time. And so being a philosopher, he looked around nature, saw things happening, and put thought behind what could cause them and how does it tie into other areas of life. So he is the first person to be recognized to idealize the existence of fundamental particles. And he referred to these simple fundamental particles as atomos. And when he thought about these fundamental particles, he believed that they were indivisible, meaning that they were the smallest form of matter that could no longer be cut down into even smaller particles. And the way that he envisioned these fundamental particles was that they existed in various forms and shapes. So some were smooth on the outside, some were bumpy, some had like things like we might call Velcro today so that they could easily stick to other fundamental particles. Then history will take us a little bit over 1,000 years later. The next big movement in atomic structure is John Dalton, and he is from England. And he works as a chemist. So he's an English chemist. And John Dalton's lifespan is from around 1766 until he passed away in 1844. So his work was late 1700s, early 1800s. So still not a lot of technology. But they did, at this point, have lab equipment like flasks, water baths. They were able to capture gases. So John Dalton, in his experiments, he collected gases produced in reactions and collected data and figured out ratios in which elements combine in different reactions. And using his observations, the data he collected, he came up with his atomic theory, which is kind of like the father of chemistry or the cornerstone of chemistry as we know it today. So one of the things is that all matter is composed of atoms. And so scientists chose to use Democritus's word. So we still use the word atoms today. So all elements are composed of these atoms, which are indivisible. So meaning, we can't use a hammer or knife to cut them into smaller bits and pieces, and they are also indestructible. So we're not able to destroy them or change them into nothingness. So are composed of these indivisible and indestructible atoms. Now he goes a little bit further and he says that all atoms of a given element, they are absolutely identical to each other. So all atoms that belong to a given element are identical, and he based this on mass. So because they have the same mass. Where he stated atoms of different elements, they have different masses. And because they have different masses, they are not identical. And then he came up with two very important laws using his data and observations that we still use today. So the first one is the law of definite proportions, and it simply states that atoms can chemically combine, forming bonds with each other, not sure if my pen is on, in fixed ratios. So the big idea here is that if you change that ratio, you change the compound. So an example would be water. And the only way to write water's chemical formula is H2O, because it will always have a 2-to-1 ratio of hydrogen to oxygen. Another example would be glucose. So glucose's molecular formula, C6H12O6. If it's going to be a glucose structure or molecule, the carbon to hydrogen to oxygen ratio will always be 1 to 2 to 1. That ratio of the elements determines the type of compound. The second law that he wrote down based on data he collected is known as the law of multiple proportions, which simply states that atoms can chemically combine in different ratios to form different compounds. So, great example, which we already stated, is water. So, water, we know its chemical formula is H2O, meaning it has a 2-to-1 ratio. But there is another formula in which hydrogen and oxygen combine in this chemical formula as H2O2 with a ratio of 2 to 2, and we do not sip this like we do water to stay hydrated. When hydrogen and oxygen form this 2 to 2 ratio, it's a substance that we know as hydrogen peroxide. Hydrogen peroxide is a different substance compared to water. From here, we move to almost 100 years later, and we find J.J. Thomson. And J.J. Thomson is also from England, so he is British, and his area of expertise is in physics, so he's a British physicist. Now, J.J. Thomson, he was born around 1856 and passed away in 1940. So in his lifespan, he saw World War I and the beginning of World War II. So J.J. Thomson, before we jump into what he discovered and all of those things, I want to list a couple of things. So at this time of J.J. Thomson, he's doing his work in the late 1800s. So, scientists, they are working with electricity. They understand some ideas with electricity and magnetic fields is that like charges repel, where opposite charges attract. But matter as a whole, when you pick up a sample of matter, the entire sample of matter is neutral. So these were ideas, things that had been established by the scientific community before J.J. Thomson started his experiments. So J.J. Thomson was playing around with cathode ray tubes, which, if you have ever seen an old-fashioned, huge, heavy TV, what produces the picture in those would be a more modern version of the cathode ray tube. And so you have a power source. So this is my power source. And you have this cathode ray tube. And near the power source, they refer to this as the cathode, so that's where its name comes from. And the opposite end of the tube is the anode. And when they turn the power source on, there's a stream that occurs, and it's actually pretty colorful. It glows. So if you turn the lights down low, you see this glowing like light wave traveling down this glass tube. And so they started playing with it, and on one side of the glass tube, they would place a magnetic plate that carries a positive charge, and on the opposite side of the glass tube, they would put a plate there, magnetic plate, carrying a negative charge. And when they put these two plates on either side of the glass tube, the beam no longer moves straight from one end to the other end. It changed its pathway. So what they noticed is when these charged plates, positive on one side, negative on the opposite side, that every time they were there, that the beam would always deflect towards the positive charged plate. So what J.J. Thomson discovered was the negative charge using that cathode ray tube. So opposite charges attract. The beam was attracted towards the positive plate. Like charges repel. The beam would move away from the negative plate. And when they would switch the positions of the plates and recollect it, wherever the positive plate, that beam would be pulled towards it and be pushed away from the negatively charged plate. So here we go. What he then concluded is that every atom has a negative charge, even though the atom holistically, matter is neutral. So the atom has a negative charge, matter is neutral. So therefore, it must have a positive charge too. Now, he discovered the negative charge, and eventually down the road, the negative charges, or these particles, were referred to as electrons, as we call them today. Now, J.J. Thomson, he envisioned what an atom looked like with his discovered negative charge and his hypothesized positive charge. He called his model the plum pudding. So an English dessert or recipe that we don't necessarily have here today in modern America, but in this plum pudding, the electrons are represented by the plums, and they are scattered throughout the pudding part, which he said was the positive charge. So his plum pudding descriptor, if we were to choose something today to represent it, maybe like a chocolate chip cookie. So in the plum pudding, the negative charge is distributed through the atom's positive charge. And because you have both negative and positive charges present, so since these are both present, the structure is neutral. So the structure is overall neutral. So a negative charge cancels out a positive charge. So when you look at the whole structure, it is neutral.